we will resume our journey from where we left yesterday. I couldn't finish a couple of slides, so first I will cover that. But hopefully, after yesterday's introductory theoretical QCD lecture by Professor Sven Molaf and the introduction what I gave, and even today's morning lecture, if you take away one message, that if you ever care about QCD and want to study them in real life, you can't avoid jets. If you deal with strong interaction, jets will form, and we sort of started tried to go through semi-analytic reasoning that why jet forms because of the Sudakov double log. You saw the same calculation of E plus E minus 2 3 jets from two different perspectives. So yesterday I just did a normal Feynman diagram and wrote down the amplitudes, etc. Today you saw that using DIMREG in the morning talk, that how the real emissions are sort of regularized, and jets will form because of the nature of the QCD radiation. So we were talking about what an ideal jet reconstruction algorithm should be. So let's start from there. So I'll recap from last lecture that now this picture is quite obvious to you, hopefully, that if you have a hard scattered pattern, the particles which will come out as end state will tend to be collimated in a geometric vicinity, and you want to have an algorithm to collect this particle, which we will keep referring now on as jet reconstruction algorithm. The first part of this talk is about what criteria a good jet reconstruction algorithm should have, and how many different jet reconstruction algorithms are there in the market, why they are popular, and we will first try to go through merit and demerit of those algorithms and why they work and where they fail. And then we will try to see rather like once you write down the theory, once you reconstruct jets, etc., how they are used, like a real life utilization of these jets. Okay. So that's where we are. So this is the Sudakov double log factor, which has been like tried to thrown at you multiple times, and that's it. So now already yesterday we were discussing that a good jet reconstruction algorithm should have IRC safety. Now let's look that statement from a pattern level. So let's say at pattern level, initially you have 3 patterns, okay, and there are 2 parallel algorithms. One of the algorithm, when applied to this 3 pattern, where the middle one is having a virtual correction and a real emission, when one of the algorithm collects all of 3, and in both the cases it call it one jet. There can be another jet algorithm. We don't know what that algorithm is specifically, but let's say some jet algorithm takes these patterns and somehow clubs the first 2 legs as jet 1 and identifies the third leg as jet 2. Now our task for this toy problem is to identify which one is a valid candidate for jet reconstruction algorithm and which one is not. So if jet 2 is a good algorithm, then you see that once you take out this part, then if you club the plus infinities and minus infinities from real emission and virtual emission, jet 2, for the case of jet 2, these 2 infinities won't cancel. So that's what it means that an algorithm is not IRC safe. Whereas for both the cases, if an algorithm jet 1 clubs all of them, then within the inside the jet there are patterns for which the real and virtual emissions cancel. So this is a good jet algorithm. So this is one of the first criteria of having a good jet algorithm, that real and virtual emission in whichever patterns are there inside the jet, that should be cancelled. Okay, so this is sort of a cartoon diagram which is given to show the context. Now, what does this thing formally means? jet will be a set of particles. So if I can define an observable related to jet, it should be an observable on a set of particles. So here you see that there are n particles, and then if there is an n plus 1th particle whose momentum or energy momentum is going to 0, which means that the n plus 1th particle is a soft particle, then a good jet algorithm should always give you a jet for which the jet observable O should return you the same number whether or not you're including the n plus 1th particle, which is particularly tagged as a soft particle, which essentially means O should be such a function such that if you pass an additional placeholder which is order of 0 versus other placeholders which are order of 1, the output of the function won't change. This is called infrared safe observable. Okay, not collinear. This is just the definition of infrared safe observable. How about collinearity? If n plus 1th particle is collinear with the nth particle, that essentially means we can sum up the 4 momentum of n and n plus 1th particle and should get the same number back. Okay, so the n plus 1 point function is clubbed to n point function, and the jet observable for n plus 1 variable and the jet observable for n variables should return you the same number. This is the definition of collinear safety. So this is the formal way we define whether it's an infrared and collinear safe, and whatever are jet observables, they should pass these 2 criteria. Okay, this is called IRC safety, and every jet algorithm has to follow it, and we will see how that follows. Yeah. Yeah, we are only making statements about 4 momentum. One of them can be photon, another can be pion.
The IRC argument is simply about the soft emission.
Yes. So it says that if you, you can also revert the arrow, which means that in a set, if you add another soft particle so that a set of n becomes a set of n plus 1 cardinality, the output of that set based function won't change. Okay. It's just a way, it's a loose way of writing, let's put it this way. What it means is strict equality. Okay. No, species, we are not talking about species at all. There is some particle A which is carrying 4 momentum, there is some particle B which is carrying another 4 momentum. Those 2 4 momentum are becoming parallel.
Yeah, but on the right hand side, Pn plus 1 refers to which one?
So that will be a placeholder for 4 momentum. Now, if you say like, if there is a species, whether my species is changing, the species will be written as the higher momentum particle. Let's say an electron and a photon which are very close by, and the photon is released at a grazing angle from the electron which is inside a jet. This can happen. Now, once you merge them, what will you call that merged particle? The convention is whichever had the higher Pt, you call the new particle at the
whichever had the higher?
Transverse momentum. That's an important variable. We will come back why it is. Okay, but let's just take this as a prescription. Okay, great. Good. Now, once these sort of criteria were fixed, people started thinking, so let's just have a global agreement in the particle physics community. What are the criteria of an algorithm to be called a correct jet reconstruction algorithm? And this is an algorithm of what? You will be given a set of 4 momentum, and that algorithm will filter them out and will return a subset of 4 momentum. This is just the jet reconstruction algorithm. And the return subset will be called jet constituents, and their 4 momentum sum will be identified as the jet 4 momentum. Okay, that's a simple algorithm, but a simple process. that is just a filtering algorithm. It's a deterministic filtering algorithm, which means that every time if you ensure the same set of 4 momentum are given as input, you will always get the same set of 4 momentum as output, the same subset. Okay. So what that algorithm should have as a good criteria, these are the following, as you can read out, that first of all, like if it's too complicated, computation heavy, essentially we can't use them. So what's the point of writing down 20 pages of algorithm if we can't use them? So let's make life simpler. We need to use them for practical measurements. Then if you define an observable, the same observable which is good to measure in the laboratory, the same observable you should be able to compute using the principles of quantum field theory. So that's a very important criteria, that it's not that two complete different things, two complete different communities don't talk to each other and they both call something as jet. That can't happen. It's the same jet, same definition, same algorithm, which should one be able to go and measure in laboratory, and the same quantity can be computed from first principles of QFT. Okay. Now, it should be well defined in some arbitrary orders of perturbation theory. Now, when you go higher orders in perturbation theory, the computation itself is hard, but nonetheless, it can't be that an algorithm returns you finite quantity at some n cubed LO level, and at n4 LO level that same observable go nuts. That can't happen. Okay. And it should return finite numbers all along the line, and finally the hadronization process, which we don't understand from first principles, so we only have parametric models which we fit from data. And there are 2-3 different hadronization models which are available, which people regularly keep on updating. They are fitted parameters. The outcome, the yield of cross sections, should be rather stable against change of this hadronization model. The last statement may have few words which are not making you comfortable, but it's all stating that if there are non-perturbative parameters at the end which I don't have control over, better the output, the end product is sort of not much sensitive to those non-perturbative parameters tuning. That's the whole statement about the last one. Okay. Good. So, given that these were the agreed choice, like criteria, which was well settled and agreed among the community, yes.
So this hadronization model is a statistical model, or it is?
No, it's a like. So there is a stochastic model. Also, there is a deterministic model. Whether it's a Hurwig versus Pythia, this kind of thing.
But then how does it remember about the initial angular dependence of the partonic level cross sections?
No,
It is a statistic.
So here you're just giving at particle level,
Okay.
right? So I mean, some cases for some jet algorithm, it's the shower is angle ordered in the parton shower, but in some cases there are also PT waiting for the showers. Okay, so but the jet algorithm typically takes the particles, the stable particles.
But it is assuming that all the hadrons are coming also collimated around the partonic initial partonic moment.
Yes. That's what like the initial theoretical input is, that no hadron can fly in completely arbitrary direction. The hadrons which came from the color neutral combination of the soft partons, they sort of lie in the same direction in space. Good. So, we have two main sequence jet reconstruction algorithm. One is the sequential recombination algorithms. We will all explain what those are, etc. And another is cone algorithm. Cone algorithm these days are not so popular. Not many uses them. But nonetheless, in the early days, in the 80s, when both of them were growing, it's good to remember that both of them had grown in parallel. And there were Atlas cone algorithm, CMS cone algorithm, sort of which no one uses. So the whole idea is that you are given the whole event, which is a set of particles. and you want to partition a set. You just look at the set distributed over eta phi, like the angular solid angle variables, and then you want to have geometric clustering. You partition the set according to the geometric vicinity, and you do all at one go. But although it was from computation point of view quite efficient, there were issues with infrared and collinear safety. So people eventually moved to sequential recombination algorithms, which are a bottom-up approach, which says, given a set, you start clustering the elements of the set from one point, like choose one element in the set and start clustering. How that happens, we will come pretty soon. And that gave sort of IRC-safe variable, but it's computationally much more intense. Okay, so let's see what are these. Yeah. So,
The scale, yeah, n to the 3.
if n is the number of initial particles which you started clustering or partitioning, what is the typical time taken to finish the algorithm to converge? That goes as n cubed, sometimes n log n, we will compare them. Okay, so that's where the computational, let's say, efficiency of an algorithm goes in. That's the CPU time.
I see. And this distance measure that you're talking about in the sequential recombination algorithm, that's a distance measure in real space. I mean, it's in the
Yes.
it's a distance measure on.
I will just come in great details about the distance. It's just showing you that two main sequence things started evolving, and eventually the community picked up one. And IRC safety played a major role to decide which sequence will survive in long run. Okay. Yeah.
So, about the NQ, so it is NQ as it is written in the textbook. So, in the textbook, if you write the algorithm and calculate the complexity, it will be NQ, but there has been breakthrough by the FastJet group. Now, if you cleverly write the algorithm, then it
It's
becomes
n
n
log
squared, n squared at, at max, but you can bring it down to n, ln n.
N log n is so initially when it was proposed, it was n cubed.
Yes, as it is written in the textbook,
Yeah.
that is, and
I mean the
naively calculated.
original FastJet paper, etc. It was, I think, the 2008 version. I have to check that, but originally it was n cubed. But then, as you said, that now there are more efficient way of this reconstruction,
Right.
and the best you can zero it down upon is n log n.
N, ln n.
Right. Great. So before completely switching to like sequential clustering algorithm, it's sort of for one last time, let's look into the cone algorithms. So the cone algorithms are sort of, you're given the whole set, you want to partition them, and there are many different partitions, but what happens is that the algorithm tries to fix, like find the hardest particle, and here hardest in the sense the highest PT particles, and then try to build partitions around them. And there were issues with infrared collinear safety, but nonetheless, there were many of them which were proposed in the market. So if you want to go back and look into what were the details of them, you can, but in this sort of lectures, I won't spend more time on them, because in modern day, none of these are actually used for measurements. Okay. Now comes the recombination algorithm. This is something which is used, so let's try to understand them at some details, that how the steps evolve. So what's the point? That you are given a set of particles, which means a set of 4 momentum, and all those particles have a location in the eta phi plane. Okay, and the definitions of pseudo rapidity and azimuthal angles are given. Why we use those quantities in lab-based experiments? Because if you have 2 particles which have eta values of say eta 1 and eta 2, so you can compute a delta eta, which is eta 1 minus eta 2. Also you can have a delta phi, which is phi 1 minus phi 2. this delta eta and delta phi quantities are invariant under longitudinal boost. So, if you are measuring something in the lab frame, the same number you can use for the partonic frame, which is otherwise non-trivial, because remember that since in a PP collision scenario, when partons are coming with certain PDFs in the initial state, the lab frame doesn't coincide with the center of momentum frame of the partons. So, it's impossible to determine where the Hertz scattering is happening, what is the center of momentum frame of the partons. But nonetheless, if we can construct variable which we can measure in the lab, and if relativity guarantees that the same numbers can be used for another frame which is just longitudinally boosted compared to the lab, so it's great that what jet reconstruction we will do in the lab and measure them, those numbers which we can use to infer interesting observables which are happening in the partonic center of momentum frame. Okay, that's why these sort of variables are used for collider physics. Right. Now given some particles are there, and this cartoon goes as the blob sizes are proportional to their energy, what we first construct that for every pair we construct this distance, which is Euclidean distance in this 2D plane of eta and phi. So, every pair has an associated number. So, let's assign some numbers to this cartoon picture. And now, yeah, sorry, eta, sorry, theta. Oh, the theta is if a particle has a 3 momentum, it must be making, the direction of the momentum must be making a polar angle with the global z axis of the system, and that's the polar angle. Okay. So, now those particles which have the lowest value of this pair Dij, let's try to club them, and let's try to club them in the sense that when we merge two particles, we call it one particle, and that one particle has the 4 momentum, which is a combination of the merger. So, if I have two particles A and B which are carrying 4 momentum of Pa and Pb, once I club them, because they are in the geometric vicinity of each other, and create a new particle which is sort of a placeholder, it is not a real particle, it is a placeholder. So, the 4 momentum which I will assign to that particle should be Pa plus Pb, as simple as that, right. And then we will continue this merging as long as all the merged hypothetical particles are sufficiently far away from each other, and whatever will be the distance threshold to decide how far they should be, that is a parameter of jet reconstruction algorithm, right. So, if I go by the figure, maybe first this 2 piece of particle will be clubbed, and then if I sort of set the threshold to be 1 unit, then surely this 2 will never be clubbed, this one will never be clubbed, this one will never be clubbed, but this 2 will be clubbed first, there will be an effective placeholder there, and then this and this will be clubbed probably, and essentially if we set the threshold to be 1 unit, we will be living with 2 large blobs. Because remember, since the 4 momentums are added, each time we merge 2 particles, the size of the blob should increase, because that's proportional to the energy of the particle, right. So, once we are done with this algorithm, the end state will be we are living with 2 blobs which are 2 jets coming out from the set of initial 4 particles, and that's it. Yes.
Order in which you pair up the particles, right?
So, first given a set, we have NC2 pairs. Each pair has a number Dij, right. So, now we scan these NC2 numbers and check which is the lowest value of Dij. We merge them. So, once we sort these numbers, we know at which order the algorithm will keep merging the particles. Okay, good. Huh?
It will be cutoff dependent.
That's what I said, that an optimal threshold of the distance scale in this plane should be a parameter of the algorithm, that how far they should be like far apart so that you don't club them together anymore. Like if those two particles, like I said, let's say 1 is the unit here. As long as two blobs are within a distance scale of 1, you are allowed to combine them. If they are not within that 1, you cannot combine them. Right? So that's why these two particles can never be combined, these two ones can never be combined, so on and so forth. Yes? Two. The number of jets will be 2, but the actual particles will be.
So if I fix R,
Huh.
it's possible that there will be 3 which are satisfying this condition. 3
Okay, if there is a degeneracy.
anything which is, suppose that R is actually 1,
R
and
is-
I have 2 R1 and R2 which are bigger than 1.
Huh?
I can have a 3-jet event. And
Yes, I mean if like
so 2
we
is one possibility. Maybe
2 is a one possibility, like given on the
you can
like
have a
the-
3-jet event.
yeah,
also.
I mean you can just initially populate this with any number of little blobs, and then whatever the
At
algorithm,
the end, you can get any number of.
any number of jets, the number has to be less than equal to the number of starting cardinality of the particles. Right? Yeah. So let's just write it down. No? If a particle has a 4 momentum p mu, which is E, px, py, pz, then the amount, the 3 vector of the momentum is this px, py, pz, blah blah, and then you have a direction theta which should be tan inverse of pz by square root of, no, it's not the tan inverse because this is the cos theta, so cotangent inverse by px square by py square. This is what the definition of a polar angle is, and the azimuthal angle phi is by definition tan inverse of py by px. It's just the spherical coordinates, spherical coordinate for every particle. If there is a 3 vector momentum, you can compute this number theta and phi. Theta is the polar angle, phi is the azimuthal angle. Okay, so if you want to see what's happening, that there is a 3D space, x, y, and z. A particle is flying in this direction. This is the direction of the momentum, and the angle, the motion of the particle is making with the z-axis. Okay, this is theta. Now, what I made a comment that why we choose this variable, by the way, this is pseudo rapidity, but for the same particle, you can define something called rapidity, which is half log of E plus Pz by E minus Pz, and it's pretty easy to show that for a massless particle, this number rapidity and this number eta, pseudo rapidity, which is defined as log of tan theta by 2, these two number coincides. However, like this number is well defined for both massless and massive particles. I mean, somewhere, doesn't matter, it's the direction which matters. It's a flat space, you set the original corner of the room here, I don't care. The directions of x, y, z are well defined, and that's what I care. Okay, great.
Sorry, about Ravindran's question. it sounds like this is the number of jets is extremely dependent on R, right? I mean, I choose R31,
course.
R2.
Yes.
So I guess there's some consensus on what you call 4-jet event as me also calling 4-jet event. So is that
Yeah.
a convention that everybody follows? I mean,
Yes, so first, number of jets should come with the jet algorithm itself. Like if I change my jet algorithm, even if I change the parameters of my jet algorithm, the number of jets will change, right? So that's, I tried to demonstrate through a toy intuitive example, right? Okay, anything more? So let's move on. Now, the first ones which were used in the lab days were KT algorithm. Now what KT algorithm was, look, earlier the definition of Dij had a thing called only the angles. Delta eta ij whole square plus delta phi ij whole square. Only these angles which are scaleless objects, but nothing said this has to be the only definition of so-called distance between two particles. You can change the definition of distance between two particles. So people started incorporating the energy of those particles in the definition of the distance, and they were normalized to keep the actual Yij dimensionless object. Okay. So let's see how they were used. Again, start from the set of n particles. So for every pair, depending on which algorithm you are trying to follow, you can compute these numbers Yij's. And also, you have to initially settle down a predefined number called Y-cut. So what is there given to you? You are given a formula to compute Yij for every pair, and you are given a number Y-cut. Now, for every pair of these particles, once you have this Yij, you try to see which is the smallest pair in terms of this distance Yij. And if Yij is less than Y-cut, which is the upper threshold, then you keep combining those particles, just as the same way we were trying to demonstrate for the previous cartoon case. Okay, so you just combine the particles I and j if the distance Yij is less than Y-cut. And you keep doing that you have a sorted list of Yij's, whatever are the smallest, first combine them. Then again start from fresh and keep combining them, okay, and go on and see, as long as this Yij less than Y-cut threshold is there, keep the algorithm repeat itself and see when the algorithm converges. And finally, when the algorithm can't flow anymore because of those pseudo placeholder, every Yij is greater than Y-cut, so the algorithm can't run anymore, you say, I'm done with my combination of the particles, and whatever I'm living with now, that's what I will call as jets. Okay, this is how, yes.
A very specific measure.
So the initial definition was for eta phi, but now the definition has been changed. The energy values have been incorporated.
Right, but in the previous picture, you are choosing a very specific measure. With respect to that measure, you are clubbing.
Right.
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 Is there any significance, or you?
So that's one of the significance I told, that this quantity between two particles, okay, is invariant under longitudinal boost. So if I can compute this particle in the lab, the same particle, the same quantity should hold good in the partonic center of momentum field. And you know, our hard scattering picture gives the actual physics, the interactions are happening at the partonic center of momentum field, right? So that's why these are the transverse variables which are used for all this lab-based physics. Great, and we sort of tried to reconstruct jets with some of the minimal energy threshold for the plus E minus KT.
Sorry.
Yeah.
What is the logic behind favoring smaller energies?
So whichever particle, so that's where the collinear multiplicity goes in, that you remember that all the particles which are close to each other, they are probably coming from the same pattern fragmentation, right? So all those close by particles, you better club them with each other and claim they are all coming from the same pattern, right? So that's where the collinear multiplicity goes in defining jet algorithm.
But why? So if we have energies that are simply smaller, the distance will be smaller, right?
There will be a correlation between the energies and the distance, and for different algorithm, the dependence is different. This is for the E plus E minus machine which it was used, okay? Because you remember the Q, the hard scale, is also a function of EI, EJs, all these numbers, the hard scale of the problem, right? It's a hard scattering which is taking place.
So Q is not a global energy scale for the whole process, but for those two particles that we're.
So for a pattern exchange, how much is the energy which has been like the S channel Q square kind of thing? Huh? Yes.
So I was saying that if there are two pairs of particles which have similar or same Dij, I mean that can happen. So is there any preference which pair it picks, or does it happen
So
often?
I think in that case, to break the degeneracy, you keep checking which has higher PT and try to recombine with them first. That's the thumb rule which are there. But Dij, of course, Dij here and Dij for other algorithms are different. So each algorithm comes with their Dij.
And so why do you choose the higher PT object?
Because like when a particle starts fragmenting, you say that whichever is carrying the highest PT, that's probably carrying the lion's share of the original pattern PT.
Okay.
In that sense,
Okay. Thanks.
that's, yes.
AT algorithm will do all this pairing momentum.
This space, whatever is defined by this,
Mental space. And previously in the cone algorithm, we were doing more in position space. So
angular space. Let's
angular space.
Yeah, so now it's still angular space, but convoluted by the energies this way.
So this has more advantage than the previous cone algorithm. Misses are less, or
So these are more IR safe. Like if there is a soft particle there, it will try to club them inside the radius in that sense. So we will walk through like which algorithm is IR safe and not, and why. When I come to that slide, you will we will have the definitions and which one has collinear IRC safety versus non-safety. We will walk through that argument. Sort of. So all these are QCD inspired quantities, right? So you can see that if here we didn't put an R angle here. So this is sort of dE by E whole square kind, roughly those kind of thing. And if you put a distance square here, then 1 minus cos theta is roughly theta square. So that's the delta theta by theta whole square kind of thing. So that Sudakov double log structure is tried to be incorporated inside this distance. Yes, of course. Yes. Yeah. No, the longitudinal boost can be arbitrary.
No, for this deltas have to be small, or
No.
can be anything?
It can be anything. I mean, this is like very simple exercise. You can parameterize a longitudinal boost 4x4 matrix in terms of rapidities, and you can easily show this statement. Yeah. Yeah, but the invariance was important because if we do reconstruct a jet based on measurements in the lab frame, I should be able to use that for making an inference in the center of momentum frame of the patterns, because I want to infer the physics there by measuring things standing at the laboratory. That's why these variables were constructed. Yeah, so these are all like parallel algorithms which were given here, sort of.
There are also longitudinal boost invariant. These
So I didn't check for each algorithm. You can go and try, but roughly they should be.
okay, and also I don't understand like okay, it's because this depends on ki what y cut I am choosing.
Yes.
So I mean the picture you were showing, let's say ki I had two jet events. So I mean depending upon this y cuts, if I choose smaller, those two will be like become many more, right?
So two jet event is after I choose a y cut. It cannot be the other way around.
Just by looking at the picture, I mean, it seems. It's arbitrary. Then
Which one is arbitrary? No, y cut is fixed after some good amount of study through simulations.
okay. So how do we decide what y cut is?
So if you have a back-to-back, say QQ bar event,
Okay.
and if you choose a y cut which in a simulation is giving you 5 jets, then you surely know that what your physics intuition tells you is not something what your choice of the algorithm parameters are reflecting. So better you reflect, like choose the y cut parameters wisely, so that for a back-to-back hard partonic case, you get back 2 jets. That's how those are fixed via study on simulations.
Okay. 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 Thank you.
Yeah, great. Now, the recombination algorithms in general have the following structure, which, yeah, okay.
These are usually not longitudinally invariant.
No, that's
Yeah.
where the IRC answer figures.
Exactly, yeah. So when
That's
we are
why-
talking about PT ordered ones, these are
That's the recombination
exactly.
algorithms. Yes.
So
That's why I just spent 2 slides and said these are not used and didn't spend time on them to explain step by step. But the ones which are used in day out life are these ones which are general family of KT. The T stands for transverse, and there the distance parameter is constructed in general this way. Okay, so there is a minimum of PTI, and to the power 2p, p is a parameter, PTJ to the power 2p, and delta R ij whole square, where this is the delta R ij by definition. Now, given that that's the distance parameter, we sort of tend to play the same game, that there is a beam parameter, okay, which is the highest pt to the power 2p into r square, where r is the jet radius parameter, which is a parameter of the algorithm itself. We keep iteratively find smallest distance, the same game which we have been playing until now, and keep recombining the particles, and we keep doing them as long as all the club jets are far away from each other by a number r. That is, the algorithm converges when no 2 particles, the pseudo particles, because we are like constructing placeholders, and no 2 such placeholders are within a distance of r of each other. Okay, and once this is done, again you sort of go back to step 2, keep doing the step 1 after another, and finally you have bunch of clusters here, where any piece of cluster is they're separated from each other by a distance which is larger than the jet radius parameter itself. And then you say I have so many number of jets when I started from, let's say, 30 input particle, and I converged on 5 jets for those 30 particles. Right. Now let's try to understand this in a bit more detail. When p is 1, it's called KT algorithm. When p is 0, it's called Cambridge-Aachen algorithm. And when p is 1, it's minus 1, it's called anti-KT algorithm. Why anti-KT? Because if p is plus 1, something anti has to be given to a number which is minus 1. That's why it's anti-KT, nothing more than that. Now you see, in the Cambridge-Aachen algorithm, the distance parameter doesn't have any dependence on the PT of the particles, whereas KT and anti-KT have. So what role does this play? Remember, when we talk about this IRC safety, what is the thumb rule we are trying to follow? That if there are soft wide-angle emission, we better throw them away. That's one-liner for IRC. And how those are taken here? That for P greater than 0, okay, when I have PT1 square and PT2 square, the minimum of PT1 square and PT2 square will always pick up the softer particle. So that's why a KT jet is more prone or is more affected by the presence of soft particles in the vicinity. Okay. Whereas the anti-KT ones, if you have two particles, one say have PT of 10 GeV and one is having PT of 1 GeV, then the minimum of 1 by 10 GeV whole square and the minimum of 1 by 1 GeV whole square will always pick up the 10 GeV candidate. That's how anti-KT tends to throw away the softer particles. And what is the role of delta Rij? If there are, for the hard particle, if there are wider angle particles, the delta Rij distance throws away the wider angle particles and picks up the ones which are in the geometric, the angular vicinity. Okay. So this distance, the role of the PT in the definition of the distance makes anti-KT less prone to presence of softer particles, and that's why we had a discussion in the morning, what is pile up or not. If you think pile up is a set of softer particles, then by construction of this distance parameter, anti-KT are less prone to pile up compared to when you make the same comparison with KT jets. In fact, that's why since KT jets pick up pile up so easily, in real life when you try to measure the pile up density, you actually try to measure the jet energy with KT jets. This is the reason. They are the ones which pick up pile up. And for Cambridge-Aachen, of course, the delta R is the only one which plays the role for measuring distances. So that's the angular ordered distance only. Okay. So I hope what is the role played by this PT parameters in the anti-generalized KT family distance is sort of clear, that why anti-KT is less susceptible to pile up the soft particles versus KT jets, etc. Great. How about the computation time? So here there is you will reconstruct jets very good, but in real life experiments there are thousands of particles which are getting created, and it's happening every 25 nanoseconds. And even if you want to construct your trigger based on which you will make a decision whether to restore an event or not, you have to first construct a jet. So if you have a perfect jet algorithm, but it takes a hell lot of time to reconstruct the jet, then probably it's not an useful algorithm. So it's also important to see which are, in terms of computation, which are more efficient. So you can see that Cambridge-Aachen and KT are for large n sort of a bit more efficient compared to anti-KT. This one is n log n versus n to the power 3/2, but for order of 100 or 1000 particles, they are sort of similar. Okay. I will, when I will upload these slides in the Indico, I will put all the citations properly. Right now I just build the slides and taking you, but the physics message should be clear. Great. So first we need to see how this clustering actually works. Yeah.
Different definitions of jets, KT, anti-KT. They have nothing to do with each other, right?
No,
It's
they're
only name
independent,
is jet
parallel.
for them actually.
All we care, we are feeding the same set of 4 vectors to them.
Because that whatever jet that you get in one algorithm
Yeah.
would look completely different if you use another algorithm.
Yeah.
Because the jet is defined with respect to that algorithm.
Right. But you naively
But it may
expect.
look, my question is actually whether, suppose I to perform these two exercise, for one with one algorithm and the other.
Sure.
in reality, do you see these results of this jets in physical, let's say, on
Real life.
a real life? Would they be very close to each other? Or
They're sort of close to each other. So
it's not that they are completely different.
Right, right. So let's define a study, a task, which can be performed by students here in like in this tutorial. Let's say you take a TT bar event or some back-to-back event, and you reconstruct a same event using anti-KT jets and KT jets. Take the leading jet from both the algorithm and plot their PT ratio as a function of jet PT. I won't think the ratio will deviate too much from identity. This can be like a number about 1 versus PT. But the leading jet PT ratio won't be so much different. Okay, after all, if they were completely different, both cannot be parallel candidates for probing the same physics. Something must be completely wrong with at least one of them or both of them. So better some standard variables, all of them try to reproduce, and then there will be like second order differences among them, but at 0th order, better they agree with each other. Okay, great. So now it's visually good to see how this clustering grows. So in the Wi-Fi plane, actually this is a plot from the 2008 anti-KT paper, that let's say you're given a bunch of particles, and the size of the vertical towers denote the energy of the particles, so the PT of the particles. Now, when you feed it to anti-KT algorithm, you see initially the clustering starts happening around the highest PT particles. So here there were the highest energetic particles, and it's not that somewhere with soft particles the clustering starts. It starts around the highest Z particles and keeps growing around them. And finally, when an algorithm converges, sort of this already tells you that in the rapidity azimuthal angle plane, how the jet looks like, all these jets. And also the shape gives you a fair idea how the area of a jet looks like, given that you have reconstructed the jets. And all these jet variables, which are mass, area, etc., you can explicitly compute them using perturbative QCD. So that's a fascinating thing. You're giving an algorithm and a set of 4 vectors. It's giving you a geometric shape back, and this same geometric shape you can compute using perturbative QCD and try to see if that matches with each other. And all these quantities you can experimentally measure in real life. So this is a fascinating test bed where you can put perturbative QCD on test. Okay, great. And finally, this is a comparison between the algorithm where you feed the same set, as Professor Ravindran was asking, that the same set has been fed to all the algorithms. You have outcome from each algorithm independently, and you see sort of the leading jets have the same locations with similar values. Their areas might look a bit different. Anti-KT is more circular compared to KT. The cis-cone are maybe more circular than anti-KT, so on and so forth. And the subleading jets, of course, have differences. But the leading jets are sort of agreeing with each other, which is carrying the most of the energy flow of the event. Okay, so this is a visual representation of how should you compare the outputs of different algorithms. Okay, great. You should call it the number of colored jets event, the number of different colors you see in this picture. And in general, you can see that the number of jets are different, which should be. But if you pick up top 2 jets or top 3 jets and then study their kinematics, the jet variables, so jet properties, those should be close by to each other. It's only the subleading jets which will start deviating from each other.
Shanmay, I think there's also an intricacy about like whether we should call a jet like more of a circular one or not, depending on whether the jet is prompt or it's emanating from something displaced.
It's about the shape of the area of the jet, right?
Yes.
So prompt and non-prompt is about, let's say, if it's coming from a secondary decay, whether it's a hard scattered from the
Yeah.
initial. So that's where the prompt versus non-prompt definition goes.
Yeah, but then like that the projection, what the jet shape is finally seen, there it would differ whether it's a circle or an ellipse.
No,
That would change whether it's from the prompt vertex or it's from a much displaced vertex.
no, let's say if you have a KT jet
Yeah.
from prompt vertex versus later radiation, it always be this irregular shaped. It can never be circular.
Yes, but anti-KT I am talking about.
Anti-KT, whether it's prompt or non-prompt, will always look this well-behaved guys.
Even for long-lived particles, for instance, like which decay quite
Okay, long-lived particles will have a secondary vertex which will change the jet shapes. a bit.
exactly. Yeah.
Yeah. So, but that's a different dynamics which is
And
pertinent.
I just wanted to like
Yeah,
add
sure.
this
But
comment.
if it's like pure QCD or given the same interaction you're comparing with, then the jet shapes are sort of independent of whether it's prompt versus non-prompt source. Yeah, I mean, you can see in the phi plane they're sort of in the antipodal locations. Yes. I mean, if you do a phi plus pi, you can see the other one comes out. So in that sense, they're back to back. Good. I think these were like QCD or TT bar. Most likely it's TT bar, where you had 3 jet events and some additional radiation. I have to cross check though, I'm not 100% sure, but that's my rough guess.
What happens if you take high multiplicity proton-proton collisions?
Fine, you will come up with a certain number of stable particles and you will feed that to the algorithm.
How do you define then the ridge, which is this ridge like pattern, where people see that there's a large spread along the rapidity region? One side of it is
So actually physical particles get produced in that rapidity region. That's why people get jet. I mean, that's the heavy ion collision pattern or whatever. I mean, it's the physics of heavy ion collision which governs that there will be particle multiplicity, particle yield in that region of rapidity as you like.
but this is seen in proton-proton also, high multiplicity events.
But
The ridge-like feature.
yeah, proton-proton is a complex thing, right? I mean, so there can be those particles. It's just what interaction at the parton level you're taking in that determines the distribution of the rapidity.
So for jet reconstruction algorithms, we normally also have a parameter like PT minimum,
Yes.
which is say 20 or 40 GeV. So in that case, do you always expect the pile-up jet PTs to be lower than
No.
20 GeV or
I mean, pile-up means additional radiation coming from the additional PP vertices, right?
Yes.
And there are other intricate things like in-time pile-up and out-of-time pile-up. So nothing guarantees that whatever additional radiation is coming from additional PP vertices, they will be always smaller than the PT threshold with which you are reconstructing the jets. So that if that was ensured, then by putting a cut, you could have ensured there are no pile-up, and then you don't need to put that pile-up dependent correction in jet calibration, which is a huge task. So it's not that easy. You really have to correct the jets for pile-up contamination, and you cannot suppress pile-up just by putting a PT threshold.
So you look for, so how do you remove the contamination? Do you look
The-
for
the-
some kind of
So
vertex?
no, it's about like given the pile-up scenario, which I will come and say, there are some average density profile of pile-ups. Now, if you can construct the jet area, if you can estimate the jet area, then you know the density times the area is amount of energy which is additionally deposited through pile-up, which is not originating from the hard vertex.
Okay.
Yeah, so that's the pile-up subtraction. We often hear the terms called charge hadron subtraction and things like that, and then subtracting neutral pile-up is also another issue. So those kind of things are quite a havoc job.
Okay, thanks.
Yeah. Yeah. Do you see that the phi of this one versus this one roughly differs by a number 3 if you go in the phi axis. Huh?
Around 3 or 4.
3-ish, right? What is your favorite number when it's 3-ish?
3 only.
3 only, right? I mean, for me it's pi. Okay, so that's why I said it's back to back. If something is phi, the other is phi plus pi, and that's the antipodal point.
Okay.
Yeah. Great. Now we have constructed these jets. What do? At least we can measure the jet PT in laboratory. Like measuring jet PT, which can be the most basic thing you can do in life, is about measuring actually the cross section. So when we measure something, when we see something in laboratory, we can always convert that yield to an estimation of the cross section, the production cross section, as long as we know the luminosity, right? Because the cross section is number over the luminosity. So this is a double differential cross section. Essentially for each PT and rapidity bin, delta PT and delta Y, this is inclusive jet. We just try to see how many number of jets are there. We normalize by the luminosity, and that's the double differential cross section. And also, this is the experimental definition of double differential cross section. The left hand side also you can measure, also you can compute in theory. The red lines in this plot are coming from a next to leading order perturbation theory with CT14 PTF sets, and it's for different rapidity pin. So you can see, and also there are with different sort of calculation at the pattern level, NLOjet plus plus, and this PH plus, this is must be PTI8, which is leading order something. So that was the 13 TV measurement from CMS. But what does it take to even perform the most simplest measurements? Okay, I just said, oh, we have a prescription to reconstruct jets. There are jets, and I just computed the cross section. Life is not so easy. Even to get this plot, you have to do actually a hell lot of task, which is once you measure this kind of energy deposits in the lab. Let's say this is one jet. This is the kind of thing actually you see. The energetic towers, the blue ones are associated tracks, and all this combination goes into constructing one particle flow jet. This is what we measure in reality. How do we convert this one splash of energy with associated track curvature into that number which matches with next to leading order theory? Okay, so there are quite few steps to go. The steps are as following. First of all, there are pile-up. The pile-up says that last lecture we said that when proton-proton collides, it's never one proton from one side, another proton from another side, keeps on like banging with each other. No, it's the 10 to the power 11 protons from one side, 10 to the power 11 protons from other side, come towards each other and smash on top of each other. Most of the proton don't collide at all. They just pass by. What is the average number of collision which takes place? That's the x-axis of these plots, the number of interactions per crossing. And the number of interactions per crossing, you can see, is pretty high. Like in 2016 to 18, the data taking was done with 30 pile-up, which means an event, on an average, there are 30 pile-ups. 30 proton-proton collisions are taking place within a cylinder which is like less than 1 centimeter in size in the diameter. Lots of vertices are forming, a huge energy splash, and from that you have to infer whatever is your favorite Lagrangian. Quite a hard task, okay. So, and you can see that the jet energy resolution actually keeps worsening with increase in pile-up. Resolution is the amount of uncertainty on this measurement. So this plot actually shows you that when there are more number of proton-proton collision happening per event, the actual measurement becomes worse, and that's expected because you just don't have clue what you're catching is coming from which vertex. and there are additional contamination. Okay, so first we have to correct for this, and here it's a demonstration that after we correct some of those, if I have a W jet, what is the typical sort of mass we get after pileup correction? And you can make it stable with respect to pileup variation. And same is true for something called tau-2-1, another piece of number which is good for jets which has two internal jets, so on and so forth. So the point of showing you these diagrams are that we have well established, very well established way that per 25 nanoseconds, when 30 proton-proton are colliding with each other, how to keep track of additional energy flow coming from the additional proton-proton collision and correct our measured observables due to that contamination. And this is a demonstration that we can do it. Yes.
How do you like count the pileups?
Pileup measurement is an involved process, like from forward calorimeter. When you collide protons, most of the particles go in a forward direction, and from the luminosity measurements in the forward detector, you can measure pileup.
So, I mean, there should be some distinguished criteria from the original, let's say, events and the pileups.
Right. So, the original hard vortex should be more energetic compared to the pileup vertices. So, you keep a threshold, like for each vertex there are tracks coming out, and whatever are the number of tracks to each vertex, you can associate a quantity called sum over pt square for all the tracks belonging to a vertex. So this is a quantity which is unique for each vertex, and see for which vertex this number is highest, and that's what you identify as primary vertex, and the rest of them you call as secondary vertices.
And how do you differ from the wide angle soft emission?
No, here there is no question, there is no jet reconstruction. Like there is a, here is my cylinder, at the center there are many collision vertices, which is like order of 30, and I am trying to figure out which is my most energetic interaction vertex. There is no jet algorithm here. Okay. So the whole point is that we have a way, very reliable way to correct for this additional PP collisions.
Shanmay,
Yeah.
so just for the audience sake, so usually when we deal with pile-up events, in this case you are talking about purely from an experimental point of view.
Yes.
But from a simulation point of view,
Yes.
when people talk about pile-up, they usually generate some like soft QCD like events, and then they use some reweighting to match it to the in-time and out-of-time events.
I think that's a very, I would say, mundane way to replicate the reality.
So what are the good ways? Could you, like, from a simulator, like from a
I-
theorist point of view,
I
is there a
think-
good way? Yeah.
I think in the geometric vicinity, just add additional proton-proton vertex which have similar amount of root S, sorry.
Right.
It's, if you think pile-up vertices are much softer vertices, that's a misconcept.
Exactly. Yeah.
So
So there's no
they're
reason
just
for it.
stochastic copies of
Yeah.
your primary vertex.
And also, like, the out-of-time ones need not be like soft at all. Like
Not at
none
all.
of
Not at
those.
all.
Yeah.
Yes.
And the second part of the question is completely different. Is that, like, with more events, like more collisions happening at an event, we have more pile up. So if we talk about, say, some future colliders like FCC, then the number of pile up
go
would
to
be of the order
400.
of like 400, 500 thousands. So like, have we already thought about ways to deal with such high
No,
pile up?
but for that, first we need to zero down on the detectors, because
Right.
first you need to study the pattern of the pile-up energy deposits in the detector, and once you have that, then you can go back and redesign the algorithm
Right.
how to correct for those pile-ups.
Okay. Thanks.
Okay. Good. Yeah.
So you're saying that pile-up events, okay,
Pile-up vertices.
pile-up vertices has the similar energy transfer like
Kinetics.
square root S as, but then you will have many hard interactions in one single bunch crossing, right?
Yes.
But then how do you say that there? It is usually said that there is only one hard, at max one hard interaction in each
there is
bunch
always
crossing.
hardest vertex, but that doesn't mean the second hard vertex is like negligible compared to the hardest vertex or the primary vertex.
I see. Okay, so I'll just talk to you
Sure.
after the talk.
So let's try to converge on this, and then our detector responses as a function of eta and is non-uniform. We have to correct for this. Okay, and then when we measure something, we have to to compare with theory, we have to do something called unfolding, which is getting rid of the detector resolution effect. Now, given the nature of audience, I don't want to go deep in unfolding. It's just whatever we measure, we need to add another piece of convolution to that, little correction to that, so that measurement is ready to be compared to the theory. You essentially try to get rid of detector smearing as far as possible. And once you do that, you sort of have nice comparison with theory. So what you see here is a ratio of the raw measurement versus different next to leading order theory for different sets of PDFs. You have theoretical uncertainties on and also measurement uncertainties on top of each other. And you see that all these colored lines, which are outcome of fixed order perturbative QFT computation, these tend to agree quite well with whatever we measure in the laboratory. So this is remarkable. Like on one side you saw for the yesterday and today that how complex those theories are. Even one real radiation can drive you crazy. And then you go to next to leading order with all these PDFs, different parameterizations, so on and so forth, resummed quantities, blah, blah, blah. On the other hand, we have our measurements which are extremely complex. Like we have to understand each and every energy deposition well in each region of the detector and convert it into a number which we can compare with theory. And after all this exercise, even for the simplest task, we have sort of a good agreement. So this is how deep you need to understand in order to make this comparison work. Okay. And once you have done this comparison, it tells you whatever you're reconstructing as jets, same algorithm can be applied for theoretical computation, same algorithm can be applied for experimental measurements. They tend to agree with each other pretty well, and you can extract meaningful information from them. From the same measurement, this is the PDF parameter extraction for light quarks and others, D quarks, so on and so forth. Okay, and typically the PDFs are given an x times fx as a function of the Bjork and x because in the PDFs there are 1 over x singularities, and you can measure alpha is running. Like my PhD was for this 8 TeV data, extracting the 2-loop 5-flavor RG running from this jet measurement data. Okay, so this is now part of PDG. So you can actually compute this beta function, see the running versus you can extract that from the data, and you can lay it on top of each other. And life is so beautiful that these two independent, one is pure theoretical calculation, one is experimental measurement, they tend to fall on top of each other. It's really wonderful once you finish this whole exercise. So this is something I wanted to show you, that what is jet algorithm, how you reconstruct jets, and at very naive level, already how many different fascinating things you can do with basic jet measurements. So from next lecture onwards, which will be probably on Thursday because I have exchanged a slot with Shankho, I will talk about jet substructure, what are their theoretical properties versus what we measure, etc., and then we will talk about jet tagging, where we will also discuss how machine learning creeps in. Okay, those will be the content of the last 2 lectures. So yeah, I will stop here today. Thank you.
One comment, like it's a follow-up of what I was already saying, that the probability of a hard event, like for one bunch crossing, it is Poissonian, right? So if I remember correctly, it goes as something like instantaneous velocity, instantaneous luminosity times the cross section of the process divided by the frequency of the LHC.
That's Poissonian as long as each bunch contains enough number of protons.
Yes, so like say 10 to the power 11, right? So that's what we have. Times, so the full formula is L times sigma divided by some F, which is the frequency, times the number of bunch crossings. So if I just put some random numbers, I just did it in the back of the envelope. So to get one top event, the probability is 0.006. To get 2 top events, it's 10 to the power minus 5. So like to get 2 top events or even 2 Higgs events, it's like very, very rare. So it's mostly between 0 and 1, the number of hard processes. And of the order of 100 soft QCD events, if I'm not wrong.
0 is useless.
0 is useless, of course. So there are events where there are 0 hard processes.
Where no proton.
Yeah, exactly. But like 1 is a good number, but having having even 2 and above, because it goes as e to the power minus of mu.
Right.
So it's very small. So to add to Taushik's point, I think having more than 2 or more, it's very, very rare.
Yeah, but also think the amount of integrated luminosity we are getting.
Yeah.
So
Exactly, right. Exactly. Yeah, but like because it goes as instantaneous luminosity, like 10 to the power minus 34.
Yeah.
Question regarding the last thing that you mentioned, 2-loop beta function and see the running in the experiment. Could you elaborate on that? How much? So from any beta function, you have to integrate it, and given an initial scale, I have to know up to what scale is it reliable and so on.
So how it's done? What is raw cross-section measurement is raw cross-section measurement. You go in the lab, measure number, and that's it. Now you lay a theory distribution on top of that, and the theory distribution is a function of alpha s at mz. Right? Now you vary the value of alpha s at mz by some numbers and see which choice of alpha s.
What is MC?
Z mass. Okay, so you need to. So now you see which number, which choice of alpha s at mz suits best with your experimental measurement. So that's the fitted value of extracted value of alpha s at mz. Now, if you are using a fixed order perturbative QCD spectrum, you can use the beta function running of the same order to extract, to evolve the alpha s at mz to alpha s at some other scale q. And that's how you get this plot.
So how far? I cannot go arbitrarily high Q, right?
So right now, let's look at the number.
How do I figure out up to which Q can I hope to?
So that's the good thing about QCD, that you know that however, like at larger Q, it's asymptotically free theory, so it will remain perturbative. So you can ask the other question, how low I can go in Q. Right?
So that's crucial here.
Yeah, absolutely.
Okay, fine. That's a question.
Yeah.
Any further questions?
This is a good.
Yes, so could you briefly go through what goes into unfolding, if possible?
So unfolding is, first of all, I think let's use the board, otherwise I don't have slides for unfolding. Let's say you're measuring an observable X, and when I say that I'm measuring an observable X, typically what you do you end up measuring some differential cross section in the bins of X, right? So I have a quantity something like d sigma dx as a function of X, and in the bins of X I have some histogram, some distribution. That's my raw measurement is, and on top of that I can lay down my theory curve, which also gives me a prediction of d sigma dx. Now, if I do a raw measurement, this spectrum is always smeared by detector resolution effect, right? So what I do, I try to construct a response matrix where the matrix is the bins of X, and here you have truth X versus reconstructed X, where reconstructed X is a quantity which is suffering from the detector resolution effects.
So X is like a variable,
A
PT or.
and eta, something like that.
So also,
So
I
this-
mean, apart from smearing, also these jet reconstruction and pile-up subtraction, all of these go in, right?
No,
To
this
get
is
the
only
final-
about the resolution. So why resolution plays a role? Because whatever at, let's say, truth level is a 100 GeV jet, it can be, it will undergo detector resolution effect, and that smeared jet PT can be either 100 GeV, let's say if it's 100 GeV, it can be 110 GeV or 80 GeV if it's a Gaussian smearing. So the same jet candidate which was landing in the 100 GeV bin for the truth spectrum will land up in a different bin in the measured spectrum. So there is a bin migration, and you want to really see from the response matrix that how much is the departure from the diagonal line, and that will give you a measure of the bin migration, right? Now you want to do an inversion of this matrix and want to apply it on the reconstructed spectrum so that you get something which can be directly compared with the truth spectrum.